Hello. Um, this is the first workshop of the Fundamentals of Electrical Propulsion series. Today we're going to be going over Introductory Thruster Principles. This is for anyone in AETHER who missed the first workshop. This will be going over these. Or if you've already seen that workshop, I'm going to be going a little bit more depth in here because I don't have the time constraint that we have at 50 minutes. Also, if you're not from AETHER and are just interested in learning electric propulsion, this is a good way to do that. I'm going to be doing a series of these lectures over all of the fundamentals of electric propulsion, and I'm trying to do this at a level that's going to be understandable by most people. There's going to be some calculus stuff in here, so it's important that you know like what the concept of a derivative and an integral is, but you don't really need to know how to solve them. We will also be talking about vectors, which it is very useful if you know those, because when we're talking about electric and magnetic fields, we're going to be going into those. Basic knowledge of electric and magnetic fields is going to be helpful as well, though it's not super necessary, and I'll go a little bit into those. I'll also probably make some videos later down the line that explain those basic concepts, like some of the stuff from calculus 1 through 3, vectors, and electromagnetism stuff more, because some of this does get very physics heavy, especially when we get into plasma physics in a couple of lectures. Starting off, this is Dan's book. It is a very, very important textbook. It's what all of these lectures are going to be based off of. It is Fundamentals of Electric Propulsion, Ion and Hall Thrusters by Dan M. Goebel and Ira Katz. It includes so much information on ion propulsion, and it is probably the best resource that I have found and that my team has found for learning about these types of topics. I highly recommend you read this book, especially if you're in AETHER and working on a specific part of the Hall effect thruster design. It's very, very important that you read the part of the book that's about that. So like if you're working on cathode stuff, the hollow cathode section, which is I believe is chapter 4, is going to be really, really important for your work. We'll go over all of it eventually throughout this workshop series, but getting a jump start on that might be helpful. The books are very dense. They require a lot of information up through Calc 3 and through Physics 2, which is electromagnetism, as well as some plasma physics stuff that you probably haven't worked on and that aren't really covered in any aerospace engineering courses, at least at Cal Poly Pomona. They might be at other places, again, if you're watching this, not as someone from the AETHER team. There's also 2 editions of this book. The first edition is the one that all of this information is based off of. The second edition just came out as free within the last couple of weeks, so I haven't had the chance to dive super deep into that. There's a lot of updates and there's a lot of new information added, but a lot of it is on systems that aren't super relevant for us right now. It's on things like HET magnetic shielding or electromagnetic thrusters, which I'm not going to go super deep into because they're not applicable to the Hall thruster system that we've made. I'll probably make some videos way later down the line on those types of systems, but it's nothing super immediate. So when following along with this, all of the section numbers are going to be referencing the first edition because there was some stuff that was reorganized. So just keep that in mind. Look for the first edition. You should be able to find it online if you just search Dan Goebel book or Goebel and Katz. Any of those should pull it up, and you can get it for free from NASA and read it online. So first thing we're going to do is go into a quick timeline of events for electric propulsion. So electric propulsion was first conceived in 1906 by Robert Goddard, and then later independently in 1911 by Tsiolkovsky, which I don't know if I'm pronouncing that wrong. But you'll see these names, Goddard, Tsiolkovsky, and Oberth, who's on the next line, thrown around a lot. They're considered like the 3 fathers of rocketry in general. They created a lot of foundational ideas that have led to all of rocketry, all of the stuff that we work with missiles and the space race and everything. We pretty much owe it to these 3 people. Rocketry was, of course, around a long time before they came around with things like fireworks, though they really revolutionized the field and kind of propelled it into modern day rocketry. The main point of this is that electric propulsion was around since pretty much the beginning. 1906, that's when electric propulsion was first conceived. That's before even the airplane flew successfully in 1908. So it's been around for a while, though we've only succeeded in making these systems a lot more recently. These ideas were later built on again by Oberth and then another guy, Cleaver, in 1929 and 1949, respectively. But these still didn't result in any full designs or definitely not any practical physical work on these types of ideas. It was still very theoretical at the time. The first full EP design was made by Ernst Strulinger in 1964, and then that was followed in 1968 by Robert John, who did the first full physics analysis. Again, electric propulsion is going to have a lot more physics in it than most other parts of aerospace engineering, especially with plasma physics and electromagnetism. In most of the types of electric propulsion, you're going to be using electric fields and magnetic fields to accelerate ions that give you your thrust. So there's a lot of stuff with that, and then those ions form a plasma, which leads to the whole field of plasma physics, which gets very complicated, but we'll go deeper into that in later lectures. The first designs used mercury and cesium as propellants. We don't use metals as propellants in ion propulsion as much anymore. They are still used in electrospray thrusters, but mercury isn't really used at all anymore because it's not the most efficient and it has a lot of toxicity issues. It's not very safe or easy to work with. Cesium is used sometimes. The most common metallic propellant we use now is indium. That's used on a lot of these FEP thrusters, though we tend to use noble gases now. Xenon's the best option, or krypton or argon, or some systems use hydrazine, which is another common propellant, though a lot less efficient than those noble gases, and that's not going to work on some of the more sophisticated systems. The first significant program was by NASA in the 1960s through 1980s. They were shortly followed by the Soviets during that same time. During the space race, everyone was kind of going for all of these technologies, trying to be the first one to get them to work. And for electric propulsion, it was the Soviets. They were the first people to launch a permanent thruster that used in some of their communication satellites for station keeping, which is one of those places where ion propulsion really shines. It's not useful for launching stuff into space, but once we're in space, it is very efficient and lasts a very long time for things that require very low thrust, like keeping a satellite in orbit or very slowly and rarely changing their positioning in orbit, whether that be altitude or where the orbit is centered on. NASA then made their first permanent thruster in the Deep Space One, which is a very, very important spacecraft because it was designed to leave our solar system, which this was the first one that did that, and it is still out there moving along. This is the other place where ion propulsion is very, very helpful because a very low thrust over a very long time will build up velocity in space where there's not much resistance like with air on Earth that's going to be slowing you down. So a very low thrust over a very, very long period of time, we're talking years and years and years, decades even, it builds up and you can get things going very, very fast to leave our solar system, like the Deep Space One. And then again, station keeping for satellites is a super common application of these types of thrusters. Starlink, the system put up by SpaceX that's providing internet now to people all across the globe, uses Hall effect thrusters in almost all of their spacecraft. So those are up there. Those are used for station keeping and similar purposes. Alright, next we're going to go on to this little graph of the different types of electric propulsion. This one is not a fully complete graph, specifically with the electromagnetic thrusters. These are the main ones referenced in the first edition of that book. The second edition does add a couple more that I will probably talk about at some point. Though these are the main ones that have either been used or thought of for a very long time. We have the electrothermal, electrostatic, and electromagnetic categories. These categories are split based on what we are using to generate the propulsion, whether it is thermal expansion with the electrothermal thrusters, a electric field with the electrostatic thrusters, and a magnetic field with the electromagnetic thrusters. So we'll move into some more about those now, starting off with the electrothermal thrusters, which are by far the simplest of these systems. The resistor jet, which is the first one, generates thrust by running fuel over a heating element. So you get the gas very, very hot, it starts to expand, and that explosive expansion of these propellants creates thrust to move a spacecraft forward. This is a very simple design. It's a lot easier to make. Very student friendly. A lot of student ion propulsion groups, including one of the ones we have in Pomona, use these types of systems because they're a lot easier to make, though they have very low efficiencies, which we'll talk about later, analyzing efficiencies of these types of things. Next is the arc jet. This produces thrust in a very similar way, except instead of running fuel over a heating element, we're running it through a high current arc. So an arc of electricity that's going to increase the temperature of this gas, which again causes this expansion of the propellant that's going to make a thrust. Next is the electromagnetic thrusters. We'll loop back to electrostatic thrusters next, because that's the one we're going to talk the most about, because it's what we're building here at AETHER. The first type of these is the pulsed plasma thruster, which uses a pulsed discharge to ionize the propellant into a plasma, and then accelerates it via an applied electromagnetic field. This is a very helpful design because you can change the rate at which the pulse discharge occurs, and based on the frequency of that pulse rate, you can change your total thrust of the system. And this allows for very fine control of the system. Is very, very helpful for some of these types of applications. The other one that is commonly talked about is the magnetoplasma dynamic thruster. We haven't really applied any of these in space, at least as a main propulsion system. The reason why is because it requires a very large amount of power. So you use a high current arc to ionize a very large percentage of the propellant that is running through the system, and this current arc creates the magnetic and electric field within itself. So you don't need to apply it externally, which makes it very efficient, but it also requires a very large amount of energy to do that. Most designs for a sophisticated magnetoplasma dynamic thruster are going to use a nuclear source as that power input, which of course isn't applicable for a wide variety of reasons. But the big thing about this is it creates an extremely high thrust while retaining the same efficiencies as ion thrusters. We will go into, in the second lecture, how that thrust versus efficiency relationship exists, and why you need a lot of that power in order to keep your efficiency and increase your thrust. Okay, now we're on to electrostatic thrusters, which is the one that we are going to talk the most about, because the Hall effect thruster is the type that I am working on building right now, and the gridded ion thruster is a very good learning tool that gives you kind of like a midpoint to understand a lot of these types of concepts. So those are the ones that the textbook goes over a lot, and those are the ones that we're going to be talking about a lot. A gridded ion thruster uses two biased grids, so each of them have an electric charge on them, different, to ionize a propellant and then accelerate the positive ions of those through a system. It has the highest efficiency of all of these systems and a medium level thrust, so it's generally a very good choice for an electric thruster. They're used a lot, and we're going to be talking about them a lot because they're very applicable, and they have a very they're a very good way to introduce yourself into these higher electric propulsion topics and discuss those types of things. So then we have the Hall effect thruster, which uses a cross field to generate a plasma. Perpendicular electric and magnetic fields will accelerate the ions to high velocities via the Lorentz force. They're very common recently. Again, we're working on building one, and all of the Starlink satellites use Hall effect thrusters. Hall effect thrusters are arguably electrostatic or electromagnetic thrusters, though they have more often been categorized as electrostatic, because even though they have a magnetic field, the electric field is what is doing the propelling. The magnetic field is only there in order to create a ring of electrons that allows us to ionize these particles, and then they slightly facilitate the positive ion movement, but most of it is coming from the electric field here. So that's the Hall effect thruster, and then the last one we have is the electrospray thruster. This is the one I was talking about that used indium sometimes recently. And it extracts ions from a conductive liquid through needles and accelerates them. So you take a crown of needles and you wet it with liquid metal like indium, and then apply a voltage to those needles, and the indium is going to ionize and generate thrust. They are very, very popular, not as popular as some of the other options, but they have a very low thrust. They're good for precise spacecraft control, not as much with movement because they have probably the lowest thrust of any of our options here. They also have the benefit, though, of taking a very, very small amount of power to run. We're talking a lot of times in the dozens of milliwatts, so very low amount of power required, which makes them a good option for spacecraft that have very tight power constraints, which we see with a lot of small satellites nowadays. This is the gridded ion and Hall effect thruster. We have the gridded ion thruster on the left. I think YouTube has this flipped correctly. And then the Hall effect thruster on the right. On the left with the gridded ion thruster. Let's see if I can turn on a little laser pointer. Yeah, I can do this. So this is our gridded ion thruster. We can see here our two biased grids we have, a positive and a negative one. Those are our screen and accelerator grids, and they are what is going to move all of these positive ions out, as well as trap the negative ions into the system, or our electrons into the system. So we have an electron gun right here that's going to be spitting out a lot of electrons. This is usually a hollow cathode. We can also see one of those over here on the Hall effect thruster, and that is a system that we already have built at AETHER. And so this electron gun is going to produce a bunch of electrons that will then interact with the neutral propellant and cause them to ionize into positive ions and then more electrons. These positive ions and electrons will then flow towards the set of grids where the positive ions start picking up some more speed. The electrons are going to be absorbed into these grids, and the positive ions will eventually be accelerated out of the system, which gives us our thrust. The Hall effect thruster is a little bit more complicated. We have that same electric field flowing from the cathode into the anode, but here we also have a magnetic cross field. So we have a set of solenoids on the outer wall and then a big solenoid in the center. This is going to create a magnetic field that is perpendicular to this electric field at all points, and it's going to extend radially outwards from the center of this. What this is going to do is it is going to cause electrons to get trapped and start moving around in a circle around this channel, which is going to create a very high energy electron ring. When we then push our neutral propellant ions into that high energy ring, they're going to ionize, and those positive particles are going to be carried in the inverse direction along this electric field and accelerated out very, very quickly. Additionally, after these positive ions have left the system, there is going to be electrons from the cathode that are also attracted to those positive ions and cause them to neutralize. This achieves a charge balance on our system. This is very important because if a charge builds up on the satellite overall, it can cause a lot of issues, both in reduction of the efficiency of these systems and also with possibly interfering with other electrical systems on board, which is very bad. With the gridded ion thruster, we have a specific cathode, a second cathode, that is going to be doing this. It's a neutralizing electron gun, and it is going to stop that charge buildup, because charge buildup, we'll talk about a little bit later with some of the plasma effects, is very, very bad on spacecraft. We'll skip past this review, because I'm going to assume you know Newton's laws. Big thing, though, is force equals mass times acceleration. The big three parameters we're going to be working with a lot of the time are thrust, specific impulse, and the total efficiency of a system. We'll go more specifically into how to derive these both in this lecture and the next lecture, but I'm going to briefly introduce them now. So thrust is the force that is applied to a spacecraft. It's what makes it change velocity. This is the whole purpose of rockets or these electric propulsion engines and thrusters, is to make the spacecraft move, and thrust is the force that is going to be doing that. Next is the specific impulse. This has a very strange unit of seconds, and it is a measure of how efficiently thrust is generated. Specifically, how much thrust you get per mass of fuel used. It's a little bit unintuitive. We will go much deeper into impulse and specific impulse in the second lecture. But what you need to know is that a higher impulse means that your thruster is going to be generally more efficient. And finally, we have the total efficiency. This is a measure of just the efficiency of the whole system, basically how much energy you're going to be putting in versus how much of that correlates to an actual increase in the thrust or an increase in the voltage or current of the beam of the system, which is the ions that are going out the end, the plasma that's going on the end. We call that the beam, and a beam or plume. And that's also very important. You want a high total efficiency because a high total efficiency is going to mean your thruster is using all of its resources most efficiently. You're generating the maximum amount of thrust possible for the inputs that you're putting in. So this is moving on. That was all from chapter 1 of the textbook, if you want to read along with that. We're now going to move on to chapter 2, which is chapter 2.1 is going to be on the rocket equation. So chapter 2 is going to go over a lot of these fundamental ideas of what we're going to be working with for electric propulsion, starting with the rocket equation. This is the rocket equation. You will learn it a lot in your basic aerospace courses. We're going to mess around with it in some ways you might not have touched before, but basically it just says that the total change in velocity, delta V, is going to be equal to the exhaust velocity or exit velocity of our particles times the natural log of the total mass of the system, which is the mass before any propellant has been burned. This is going to be the mass of the spacecraft itself, m sub d, plus the mass of all of the propellant on board, divided by the final mass of the system, which is going to be just the mass of the spacecraft after all of the propellant is burned up. And this is going to give us our total change in velocity. When you're designing for space missions, a lot of the time we talk in terms of delta V, because it's when you're looking at maximum speeds that you need to reach between two orbiting bodies, delta V is really what we're going to be looking at. When you do trajectory calculations, NASA has a good website for them, or when you do them by hand, a lot of the time you're talking about what's going to be our total change in velocity. Can we have an engine that fits that? If we can't, how can we change our orbits, change our trajectories, so that we can get there within a timely manner with this lower delta V limit. So this is a very, very important type of equation because we can find how far basically our spacecraft can fly. If it will let me go to the next slide. Here is two equations. So on the left side we have force equals mass times acceleration. This is Newton's second law. And over on the right we have momentum is equal to mass times velocity, which I think is pretty much just as important of an equation, especially for electric propulsion, as force equals mass times acceleration, because they're a lot more closely related than a lot of physics classes will teach you. So we will move on to the next slide. We're going to work on an example with momentum because, again, it's very, very integral to how these types of problems work. So momentum is going to describe the total change in mass and velocity of an object. So let's say we have a 10 kilogram spacecraft that is moving at 10 meters per second to the left. And then we can say that its total momentum, P, is going to be 10 kilograms times 10 meters per second, which is going to be equal to 100 kilogram meters per second. Now, let's say we lose a kilogram of that mass. It's going to start going the other direction because we've ejected it from our thruster, and it's going to be moving that direction at 5 meters per second, or negative 5 meters per second if we're talking relative to our original velocity vector. And that gives us our original spacecraft still has 9 kilograms of weight left to it. but we don't know what speed it's going to be going at. We don't know its velocity. So that's something that we wanted to figure out using consideration of momentum, because momentum, as long as you're not using any outside forces, is going to stay conserved in the system. So we can say that our total momentum, 100 kilogram meters per second, is going to be equal to the momentum of the spacecraft A and the ejected propellant B. And we know that the ejected propellant B is a mass of 1 kilogram and a speed of 5 meters per second, which gives us a total momentum of 5 kilogram meters per second, again in that rightward direction. And then we can use this equation of our total momentum is equal to the momentum of each of the systems to solve for that momentum of A. So we have 100 minus negative 5 is going to be 105 kilogram meters per second. Moving on from that, we can say that momentum is equal to mass times velocity, which is going to be equal to that 105 kilogram meters per second. Excuse my typo there. Let me fix that really quick. That should not be there we go. Sorry about that. So we can say that, where's that 9 coming from? Hold on. Oh, sorry, yes. 9 is the amount as the weight of the A kilograms. Sorry, my typo threw me off. So we know that 9 kilograms times our velocity is going to be equal to 105. So 105 divided by 9 is going to give us our total final velocity of 11.7 meters per second. So we can see that without applying an outside force, technically in a traditional physics sense, we've increased our velocity just by getting rid of a section of our mass and throwing it away in a specific direction. This is the fundamental way that thrust works. We're going to be taking a mass and then accelerating it outwards from the spacecraft, which is going to be applying a force to our spacecraft, causing it to move in the other direction. So that's our final answer. So this gives us, we have this original equation, momentum is equal to mass times velocity. In the previous situation, we were ejecting all of that mass instantaneously, which isn't really going to be happening. We're going to be ejecting that mass very, very slowly over a long period of time. So when we look at momentum, we can say that momentum, the final units of it is going to be kilograms times meters per second. This is very visually apparent. And kilograms times meters per second, if we divide it by seconds again, since we're, again, changing that mass over time, that change in momentum over time is kilograms times meters per second squared, or newtons, which is the units for force. So we can see that a force is really just a change in momentum, and this is going to be equal to our thrust. This is a definition that I really want you guys to remember and pay close attention to, because it's not covered in a lot of physics courses, not emphasized, I guess, in a lot of physics courses, but it is at its core what a force is. Force isn't just mass times acceleration. A force is a change in an object's momentum. And anytime we are changing the momentum of an object, whether that be by increasing its velocity or changing its mass, which results in an increase in velocity, that's still going to be a force. So this now kind of paints this rocket equation in a new light. We're talking about changes in velocities on the left side, and we're talking about these changes in mass on the right side, and those changes in mass times this velocity is going to equal that change in velocity, which means that the rocket equation is applying a force on a system, because we're changing mass, we're changing velocity, which means we're changing the momentum, which means we're applying a force. So that's where this is coming from, out of Newton's second law, and it is how we can change an object's velocity based on changing its momentum. So this is a very important equation for that. Next, we have the definition for specific impulse, which again we're going to derive later, but impulse is equal to the exit velocity divided by g, which is just the gravitational constant for Earth, 9.81 meters per second in metric or SI, which is what we'll be using a lot of the time here. We will jump around with some different units, especially when we get to pressures. But generally, in this type of stuff, we're going to be sticking to metric instead of the U.S. customary or imperial systems. And we can use this to substitute into our velocity equation to get that the total delta V is equal to the specific impulse times g times that natural log argument. And this is very helpful because generally when we have a defined thruster spacecraft, we can find its specific impulse and calculate that pretty easily. Again, we'll go into that later. And so giving this equation lets us find that total change in velocity based on the impulse or efficiency of the system times that final initial mass, and we don't have to worry about the exit velocity of the particles in the thruster. Another way we can reorganize this is in terms of the mass of the propellant. This is very useful if, again, we have a defined spacecraft and a defined total velocity change that we need for emission. You can just kind of plug these all in here and it'll tell you how much mass of propellant you need through the rocket equation, and it accounts for all of those changes of the mass changing slowly over time through the exponential. And this one's going to be very helpful if you're trying to figure out, based on a mission, if you have like a fuel tank that's going to be a little bit bigger from the mission, how much you got to fill it up in order to complete that mission. And of course you want to have a little bit of wiggle room there, but this will pretty accurately tell you how much of that noble gas or of that hydrazine you need to put onto a system in order for it to go. Alright, next we're going to be going into section 2.2 of Dan's book, which is on force transfer. This is going to describe kind of how those forces are generated on an electromagnetic scale in each of these thrusters. So we'll start off with the gridded ion thrusters and then do the Hall thrusters really quick. This is a little bit more complicated stuff, so it's okay if you don't understand all of this fully. I'll try to do my best to explain it, but you might have to read the book or learn some more prerequisite knowledge in order to fully understand it. So this is, again, our gridded ion thruster. We have our positive and our negative grid, our screen and accelerator grid, and we are going to be running our positive ions into that set of grids that's going to then accelerate it. We have Coulomb's law right here, which says that our force is going to be equal to the charge of each of those particles divided by the distance between them squared, or radius squared. And this is going to give the total force that those particles apply onto each other. If they are both the same sign, so both positive or both negative, it's going to be a repelling force. If they are differing in sign, it's going to be an attractive force. We can also say that this is going to be equal to the charge of whichever particle we are analyzing times the electric field which it is in. This is especially useful if you have a very large electric field that is going to be stagnant. So it has enough weight that that particle isn't going to be moving around, or in the case of our screen and accelerator grids, you have a big piece of metal that is going to be creating an electric field, and the force from the ions on that metal is going to be negligible in our final calculations. So we can just look at the force that those grids is putting on the particle. So we know that our thrust here is going to be the force of all of these ions, and that ionic force is going to be created by two of these electric field accelerator grids, the screen grid and the accelerator grid. These charged grids, we run a current through them, and that is what's going to create our electric fields. So then we can break these down into electric fields. But first, because we are working with a bunch of particles and not just one specific point particle, instead of using the charge of that particle, we're going to have to look at the charge density of the plasma. So we have a bunch of these positive ions coming in, and we can use Q if we just had one of those ions, but because we have multiple ions, it's going to be a charge density, which is used with sigma a lot of the time, and this is just going to be the vacuum permittivity constant, which is epsilon sub naught, times the electric field that it's in, and this electric field will be either the screen electric field or the accelerator electric field, because those are orienting those ions in a specific way. So we can say that the force from just the screen section is going to be equal to that charge density, which is the
epsilon sub naught times the electric field of the screen times the electric field of the screen itself. Again, remember, because we're using Q times E, or epsilon naught times E, which is going to give us an E squared. And then if we apply the same thing to the accelerator grid, and because they're opposite charges, we're going to subtract them from each other. So we get thrust is equal to 1/2 epsilon naught E squared minus E squared for the screen and accelerator specifically. The 1/2 comes out of the full derivation for the system, which again is in the book, but I'm not going to go over here. So this is the total thrust to magnitude for a gridded ion thruster. Next, we'll move on to the Hall effect thrusters, which we already described that circular motion. This comes from an E cross B field, which is vector math stuff. And this is basically when you have an electric field going one way and a magnetic field going the other way, the particle within it will start moving in a way perpendicular to both of those systems. And because our magnetic field is constantly staying at a radial direction from the center, when our particle moves a little bit, the magnetic field is going to orient, and that is going to cause our electrons to orbit through the channel with this circular motion. This is also then subject to the Lorentz force because we have a moving particle through a magnetic field, which is going to create a force with that V cross B, as well as we have the electric field itself still creating forces with the Q times E. So Q times E plus that V times B force is going to be our Lorentz force, which is going to create that total electron movement. And because of this, when we have positive ions impact, we're going to have something called our Hall current, which J Hall is an impulse, and this can be defined as the negative electron constant times the number of electrons times the velocity of those electrons across the B field. Then this is our J Hall across B field. This is going to be the total energy in that ring system that is then going to be imparted onto those positive ions that are then accelerated out of the system. I probably did a little bit bad of a job explaining that, so maybe read the book on that, because I'm not the best at articulating sometimes. Now we're going to move on to section 2.3, thrust, and we're going to just be going over the first part of this because I ran out of time in the workshop. So I'm not going to go over it until the second video when we're talking about efficiencies and corrections. So the first part of 2.3 is what we're going to be going over. So thrust, again, when we go back to that previous equation, when we're talking about thrust, we're talking about a change in momentum, and momentum is equal to the mass times velocity of a system. Specifically here, we're talking about m sub p, which is the mass of the propellant, and the exit velocity, v sub ex. And then we know that the thrust is going to be the rate of change of this. This is d over dt. And a lot of the times you'll see this d over dt become acceleration. We're talking about a change in velocity, and the time derivative of velocity is going to be acceleration. But we're going to be doing something a little bit unintuitive here because the exit velocity of an ion thruster is very predictable and pretty constant for a specific set of inputs. So instead we're going to be taking the time derivative of mass here, and that's what we're going to be analyzing, which is going to give us that our thrust is equal to the mass flow rate times the exit velocity of our system. And so this can also then be written as MIVI, because really, while we're putting a lot of propellant through the system, the only stuff that we care about is the ones leaving the system, which is just going to be our ions that get accelerated out of the either grid or the end of the Hall thruster. And making this distinction, because those are pretty much virtually the same, is very important, because when we're talking about ions, they have charges, so we can measure their currents a lot more easily. And we can also use systems and tooling in place to measure their velocity based on how they interact with the electric field generated by the ions. So we choose to define them as the mass flow rate of the ions and the velocity of those ions because it's a little bit more accurate and a little bit more measurable. If it will let me switch slides. Next, we're going to be talking about jet power. This is going to be a quick side note. We'll go a little bit more into jet power in the second workshop. It's included in Dan's book in this section, so I'm going to bring it up. But it's something that's mainly used for efficiencies later in the chapter that we'll talk about later. We're not going to get super deep into it, but basically just understand that our jet power equals 1/2 the mass of the ions times the velocity of the ions squared. Again, we'll look at that more in depth later. Now we're going to start looking at the electric thrust equation. So this is our equation. Thrust is equal to mass flow rate times velocity. This is going to be used a lot in all of aerospace, but mass flow rate of the ions and velocity of the ions, well, again, we can measure those. There's going to be some other ways we can define it in terms of currents and voltages that are going to be a little bit easier to understand and find. So the first thing we can do is say that the velocity is equal to the square root of 2 times the charge of the ions, which is pretty much just going to be 1 for most circumstances. We'll get into when it's not 1 later, times the voltage of the beam divided by the mass of each of those ions. And again, the derivation for this whole thing is in the book. I'm not going to go super deep into it, so you're just going to have to trust me. If you want that full derivation, again, this is chapter 2.3 of Global and Cats, and it'll go into that. Additionally, we can look at the mass flow rate of the ions as the current times the mass of those ions divided by the charge of those ions, which is, again, pretty much just going to be 1 all of the time. And we can use these to adjust our equation into this system by plugging in the mass flow rate and the velocity and solving them around a little bit. We get that the thrust is equal to the current times the square root of the voltage times the square root of 2 times the mass of those ions divided by the charge of those ions, which again is pretty much always 1, though it fluctuates a little bit. And this gives us our final equation. So you can see that there's definitely a lot of change that has happened, but being able to measure that current and voltage of the beam is a lot easier than being able to measure just the mass flow rate with velocity. And it allows us to have a much more accurate understanding of what the thrust is, based on very accurate tooling that we have that can check those currents and voltages. And then again, that 2m over q is going to be pretty much a constant value for any given propellant that we're using. Speaking of which, if we plug in values for those specific propellants, we can get this handy little chart, which is going to tell us, based on what propellant we have and the current and beam voltage, what our system is. We can also very easily look and see which of these is going to generate the most thrust for a given power input based off of this. We use krypton in our ion thruster, or our Hall effect thruster at AETHER, because we couldn't get xenon for a lot of reasons, but you can see that that's a very middle of the road efficiency level. The lowest efficiency here is going to be the hydrazine. That's used pretty rarely. We'll go into some of its use factors later, but never in Hall effect thrusters or ion thrusters. Argon is a little bit worse than krypton. Xenon is a little bit better. A lot of those noble gases, they do have big differences that add up when you're doing stuff in space, but at a testing level, we can kind of extrapolate what the xenon efficiency would be. And that is, oh, I think the thing broke. That is going to be the end of this lecture. So I hope you guys enjoyed and learned a little bit from this. Sorry for some of the hiccups that have happened. It's been a little while since I've recorded a YouTube video, and it's very late right now. I think it's almost 1 a.m. So my brain is starting to get a little bit fried. But if you guys have any questions, you can either comment them on this YouTube video, or if you're in AETHER, email me or post in the Discord, and I'm happy to help out with any information you may have. And the the workshop number 2, which is on thrust efficiencies, correction factors, and neutral densities and ingestion, will be out hopefully soon. I was going to film them both back to back, but again, it's almost 1 a.m. right now, and I do have class tomorrow morning, so I'm going to sleep. but that should be up this weekend if I have time. So yeah, hope you guys learned a lot from this video, and have a better understanding of some of those basic principles for ion propulsion now. So we'll be diving a little bit more deeper into why these equations aren't fully correct next time, and how to fix them so that they're a little bit more close to reality. Have a great day. Goodbye.